Hello, and today I'll be presenting the work Time-Sensitive Intermittent Computing Meets Legacy Software. This is a work that was presented at ASPLOS 2020 conference. And yeah, so first, before getting into the work, let's understand what energy harvesting is. So most legacy computing systems that are present today, they run on continued power. That is the assumption that the power that they get will not have breaks in between. This is either provided by the electricity that we get or by the batteries that are present. However, we've known since long that lithium ion batteries, which are the most common batteries used today, are very harmful for the environment. Their mining process as well as their production process creates a lot of waste in the environment which should not be accumulated. One key competitor to this is that free energy sources are available in the environment which can be used to run computing systems. For example, there's wind energy, there's solar energy, radio waves, or even the motion of our motion, whose energy can be collected and harvested to run systems. So the one question that we can ask is that what is the alternative to batteries? So a very popular alternative that has come up these days is capacitors. Now, capacitors are used to save energy between them for a small duration of time. The difference between capacitors and batteries is that capacitors hold much less energy and they dissipate it at a more faster rate. So they charge themselves, then that energy is used up, and then they can be recharged again. However, even this small energy is very good for a lot of tasks that are run on small embedded devices. Now let us understand what intermittent computing actually means. So intermittent computing is computation that is performed over non-continuous power cycles and across power outages, for example, that we saw in the case of capacitors. So let us understand this in terms of two graphs. So if we had like a normal continuous power computation system, and it is running on harvested energy. So let's say there is a progress time graph. Then this normal continuous power system would accumulate some progress as power comes up. However, as the power runs out and the capacitor is recharged, during that time the progress would drop down to zero, and when the power comes back up again, the computing system would start from scratch again, and this would keep continuing over power outages. That is, there is no way to know how much progress was made before this power outage happened. However, with intermittent computing systems, what happens is that some progress is made while the energy is available. And during the downtime, nothing happens on the system, of course. But when power comes back up again, the system somehow knows that it made some progress through previous power cycles, and it continues its computation from there, finally actually reaching its completion time. Now, this is very useful as this allows us to perform computation across multiple power cycles in case of battery-less systems, as we discussed. So now let's talk about the different techniques that are used to perform intermittent computing. So there are two very popular techniques of performing intermittent computing today. So the first one is task-based intermittent computing. So now a natural way to think about intermittent computing is in terms of smaller tasks that a program has to perform. So for example, a big computation task can be divided into smaller tasks on the basis of their energy requirements so as to complete one task within a power cycle. Make sure that it completes. This would mean that we just need to know whether the previous task was completed or not in order to continue execution after power failures. And this technique is called task-based intermittent computing, which basically transforms a big program into idempotent tasks which can be carried out independently in a power cycle. The other technique is called checkpoint-based intermittent computing. Now, this is a popular technique which employs checkpointing the program state after based on some factor like after a certain time or at a certain point during the energy cycle, and saves this checkpoint in a non-volatile memory segment. When the power comes back again, this checkpoint is used by the intermittent system to restore the program back to its state right before the power went out. This allows it to continue executing even through power outages. Now let's look at some limitations that these two popular computing paradigms have. So task-based intermittent computing has an obvious big limitation that it requires a lot of programmer support for task identification. Unless a programmer can confidently change its program into smaller tasks, task-based intermittent computing would not be very effective. Also, the current models of task-based intermittent computing actually cannot handle a lot of C constructs like pointers due to static memory model. And this makes porting legacy software to this model a big burden. Now, checkpoint-based intermittent computing, on the other hand, adds large performance overhead to the system, and it also leads to a lot of memory and time-based inconsistencies that we look at. So the first inconsistency that we look at is a memory inconsistency, which is called a read after write violation. So consider a case in which len is a variable that is stored in a non-volatile memory segment. Now we make a checkpoint right before these two lines of code r1 equals len and len equals r1 plus 1 are executed. Now, right after executing these two segments, power runs out and the system goes into a halt state. However, these two lines had already executed, so the value of len in the non-volatile memory had already changed. However, the checkpoint was right before it, and when the power comes back up again, we actually continue our computation right from that line, which is right before r1 equals len. This would mean that the value of len, which would have been something else, actually is increased by 1, which is len equals len plus 1 right now, when it shouldn't have been. So this is a write after read violation, and one way of thinking of fixing it could be adding a checkpoint right after, every read to such variables, such non-volatile variables. Now we look at some timing inconsistencies that can happen in such systems. So the first is a timely branching violation. Consider a case in which we make a checkpoint right before getting the time. And let's say that this time is also stored in a non-volatile memory and the variable is called t1. Now the program executes and it checks whether this t1 time is less than a specific time t or not, and it does calls the function 2x. Now power runs out again. And now if this value t1, which was computed actually prior to power running out, is used and checked against t, then even though the current time might be greater than t, then both of these still, this branch would also be executed, which would be incorrect. Another problem that occurs is called time misalignment, and this is a common problem in devices that use some kind of sensing or that are made for sensors. So, for example, if we want to combine a timestamp and the data that the sensor has calculated, then we would first get the time t1 and we would get the sense data. Now, let's say that we checkpoint right after getting the time, but power runs out. Now, after the power gets back and we rebooted, we use the sensor and get the data that we want. But now we classify the data D with timestamp T1. However, this T1 timestamp was probably calculated much before the data was sensed, and it could even be hours, and thus there is a misalignment between T1 and the data that was sensed just now. Now, the final time inconsistency that can happen is called data expiration. Now, this happens if uh, especially for sensors where you do not want to send data after a long time and after a long time that's been calculated to save computation cycles. So for example, let's say that we get the timestamp and we collect the sensor data in the same power cycle. However, power runs out, and after it is rebooted after a long time, then we classify this data D, but and send this classification or whatever post processing we've done. However, this data that we're sending now is actually fairly old compared to when it was computed, and we might not need that. So that is an issue that could happen. So in order to deal with the issues that we discussed, as well as the existing problems with intermittent systems like task-based or checkpointing, the paper comes up with a new intermittent system, which is called time-sensitive intermittent computing system. In brief, TIX, it's called TIX, and it is a checkpoint-based system, but it adds a few extra features and capabilities to intermittent computing, which can be used. So to look at a little bit about its uh, s- mm, features, so one of the things that it adds is it adds features to it supports all the C features, like it supports global variables and pointers, which are not actually supported by task-based computation, or it also supports recursion, which can become an issue in checkpointing systems because of large data to checkpoint. It has a technique, it uses a stack segmentation technique in order to ensure that the data that is checkpointed is constant in size, ensuring that none of the checkpoints actually exceed the non-volatile memory space on which to checkpoint. It adds a new attribute or extension to the C language in order to support time annotated decision making. This helps us solve the three time inconsistency issues that we discussed. So first, what is the architecture of the entire TIX? So uh, in TIX, the programmer is actually provided with annotations in C language, like we see here, which is the at expires after, or the at equals to, or the at expires construct, which are used to define our timing consistency constraints that we want in the program. So the first step that happens is the instrumentation. Now, at this point of time, Tex actually reads the C source program and it converts the text annotations into a valid C program. For example, the at expires and at expires after constructs are actually converted into a if statement, or correct or checkpointing calls at correct point are inserted into the program. Now, this this modified or instrumented C source code is provided to the TIX compiler, which compiles it along with the TIX runtime, which has the timely execution, stack segmentation, checkpointing, and memory management features, and produces a binary which can be intermittently executed on a microcontroller. Now we'll look at how the TIX checkpointing and stack segmentation works. So first up, to understand stack segmentation, uh, TIX says that at any checkpoint, the any intermittent system need not checkpoint the entire stack at that point, and it only needs to basically checkpoint a small segment of the stack. For this, TIX divide the entire stack size or the stack data into different segments, and the largest size of a stack segment is actually equal to the largest stack frame that a program can have, and it is determined at compile time. Now, when a function is called, in which case the stack grows due to addition of local variables as well as return values and arguments, X at runtime checks whether the new stack that is actually used is within the current stack segment or not. Now, if it is not in the stack segment, then TIX actually updates its stack segment to point to the next segment. Similarly, if a program returns from a function, a stack shrink procedure is called, which updates the stack segment pointer inside TIX to point to the correct segment of the stack. At any checkpoint, point in the program, only the current stack segment of the program is stored. This is because this is the active segment that is used, and any segments before this or after this would have already been checkpointed due to the nature of stack segmentation. And this current segment is then stored to the non-volatile memory, of course. Now, let's talk a little about how these timely execution semantics that we saw, like at expires and everything, work. So the first attribute that we can look at is the at expires attribute, which allows adding a timestamp to a value. So here we can actually specify how long a value is valid for example, 1 second, 2 second, or any other value. Now, text also adds a add timely clause, which are actually used to perform timely branching. So any annotated value with at expires can then be used in add timely in order to check whether the timestamp value has expired or not, and or any other constraint that the user wants can be added there. Tix also allows, in order to deal with the data misalignment inconsistency issues, it it introduces a atomic assignment operator at equals to, which ensures that the data is actually assigned along with its timestamp in the same power cycle and checkpointed. Now, talking about TIX implementation. So TIX is implemented, of course, as a compile time and as a runtime support system. So at compile time, TIX makes a lot of changes to the program. It instruments it and optimizes it, adding checkpointing code as well as calls to the checkpointing system in the program. The memory management also has what is called an undo log, which is actually used to store writes to writes to global variables between different checkpoints times. So this can be understood as follows: that let's say that we checkpoint at point A and we make two writes to global variables x and y. Now these are stored, their original values are actually stored in the undo log, which is present in the non-volatile memory. And if power runs out before the next checkpoint, then after power is restored, the value of x and y are restored back from the undo log. That is, the undo log is emptied out and the values of different global variables are set to what they were right at the checkpoint time, which is stored in the non-volatile memory. Similarly, if the next checkpoint happens after point A, then the undo log is still emptied and all the data that was there is discarded as the data has been written to now. Yep. So now talking about evaluation. So TIX is evaluated against both task-based and checkpoint-based systems. So on task-based systems front, it is evaluated against Ink, Mayfly, and Alpaca, and it is compared against the Chinchilla checkpointing system. Evaluation is done on three different benchmarks, popular benchmarks like bit count, cuckoo filter, and active recognition. And the parameters for evaluations are memory consumption that TIX does, as well as the execution time performance. Now, looking at the execution time performance, so the plain C execution time is taken as the base, then the Ink, Alpaca, both of which are task-based computing systems, are presented, as well as there is a naive execution time, which is the execution time of a naive checkpointing system, which checkpoints all the stack, all the global variables, and everything into the non-volatile memory, adding large overhead. So as we can see that TIX performs comparatively well compared to the task-based systems and much better compared to the naive systems. But the added support that a programmer has of not converting their program manually into a task-based setup is the major advantage that TIX has over these task-based approaches. The memory consumption evaluation is to see how much memory the TIX system consumes, as well as how much modification or changes TIX has compared to other intermittent systems on the binary size. So for example, compared to Chinchilla, TIX does much better both on the instrumentation, that is the dot text size, as well as the memory that it uses for uh, saving the checkpoints. It does relatively well compared to even Ink, and actually is much better than Ink when compared to just the dot data section. Finally, TIX also evaluates itself on basis of the time consistency violations that occur. And the evaluations show that with TIX, all the time consistency violations are actually reduced to zero. So it does produce a time consistent program. Thank you.